A common problem of integral calculus is to find the area between a curve and the x-axis. For example, finding the area below this function f of x and the x-axis from a to b would be the area of this shaded region. In the past, you may have estimated this area using rectangles. If you were to use 4 inscribed rectangles to estimate the area under f of x, it would be the sum of the areas of these 4 rectangles. As you can see, this area would be less than the actual area between the curve and the x-axis, and the margin of error is quite large. There is a significant amount of area that is not being accounted for. Now, because of their shape, trapezoids provide a much better estimation of this area. As you can see, the sum of the area of these 4 trapezoids is a much better approximation than rectangles for approximating the area between this curve f of x and the x-axis. In this video, we will discuss the trapezoidal rule, which is based on this idea. Considering this function f of x having this graph, the area, the exact area between this curve and the x-axis from a to b is provided by the definite integral of f of x from a to b dx. However, not every function can be easily integrated. For example, the integral of the square root of x to the third minus 1 from 1 to 5, or the integral of the sine of x squared from 0 to 2 are somewhat difficult. In fact, they simply cannot be integrated using basic integration methods. In cases like these, sometimes it is useful to estimate the definite integrals. One way to estimate a definite integral is with the trapezoidal rule. As I said earlier, another way to estimate definite integrals is by calculating the area of rectangles drawn under the curve and then adding up those areas. But trapezoids provide a much better estimation in most cases. The sum of the area of these 4 trapezoids is not the exact area under the curve f of x between this curve and the x-axis, but it is relatively close. To understand where the trapezoidal rule comes from, we will begin by estimating the area between a function and the x-axis using trapezoids. Here we have the graph of the function f of x equals x squared plus 1. Let's estimate the area between the curve and the x-axis from x equals 1 to x equals 9. And we'll do this using trapezoids. The more trapezoids we use, the better our estimate will be. However, using more trapezoids requires more work. It's a trade-off. In this example, let's use the 4 trapezoids that I had displayed earlier. Each of our 4 trapezoids has the same general shape. Each trapezoid has one pair of opposite parallel sides. We'll call those sides h1 and h2. And the distance between those sides is the width, w, of the trapezoid. Note that the value of h1 and h2 differs for each of our 4 trapezoids, but the width of each trapezoid is the same. The width of each of these 4 trapezoids is the same. Their heights differ greatly. The purple trapezoid has heights far greater than the heights of the red trapezoids, but the red and purple trapezoid have the same width. Recall the formula for the area of a trapezoid. The area of a trapezoid is width times basically the average of the 2 heights. Width times the quantity of h1 plus h2 over 2. Again, the value of h1 and h2 will vary by trapezoid, but the value of w is the same for all 4 of our trapezoids. How wide is each trapezoid? Well, the trapezoids cover 8 units from x equals 1 to x equals 9, And there are 4 of them. So the width of a single trapezoid is the difference between 9 and 1, b minus a, divided by the number of trapezoids that there are, which again in this case is it goes from 1 to 9. So the width of a single trapezoid would be 9 minus 1 divided by the number of trapezoids we have, 4. Therefore, each trapezoid is 2 units wide. And that's pretty clear to see. We have the graph here, and you can count the number of units on the x-axis to verify that each trapezoid is 2 units wide. Using this information, let's now estimate the area by adding the area. Let's estimate the area below the curve in the x-axis by adding the area of the 4 trapezoids. The red trapezoid's area, the total area, is approximately the area of the red trapezoid plus the area of the yellow trapezoid plus the area of the green trapezoid and the area of the purple trapezoid. The area of all 4 trapezoids will have the form W, the width, which is 2 for each one, times the quantity of H1 plus H2 over 2. So all inside the parentheses, there will always be a divided by 2. That comes from the formula of the area of a trapezoid. Let's go from the purple trapezoid backwards. The area of the purple trapezoid can be described as 2, which is its width, times the quantity of, well, H1 over H2 comes from the height above 7, and this curve is defined by x squared plus 1, so that would be f of 7, and the height, the ending height, H2, the longer side of the purple trapezoid, is above x equals 9. So that would be described by f of 9. This is the area of the purple trapezoid. How about the area of the green trapezoid? Well, the green trapezoid's first height is above x equals 5. So how high is the curve at x equals 5? Well, we have f of 5 to describe that. And the end, the second height of the green trapezoid, H2 for the green trapezoid, is above x equals 7, f of 7. For the yellow trapezoid, the lower height, the first height, the leftmost height, f of 3, and the rightmost height is f of 5. So that area of the yellow trapezoid comes from 2 times f of 3 plus f of 5 over 2. This is, again, for all of these trapezoids areas, I'm just using this formula, the width, which I found to be 2 for every trapezoid, and then I'm using the function to describe H1 plus H2. The beginning of the yellow trapezoid, f of 3, the height at the end, f of 5. For the red trapezoids, the H1 is f of 1, and H2 is f of 3. So here we have a formula for the area of the red trapezoid. Adding all 4 of these areas together gives you an approximation of the total area between this curve and the x-axis. Now, notice that in each consecutive trapezoid, the second term in the numerator is equal to the first term in the next numerator. F of 3 ends the area, the numerator of the area formula for the red trapezoid, and begins the numerator in the area of the yellow trapezoid. Yellow trapezoid's formula ends in f of 5. Green trapezoid's ends or begins at f of 5. We'll use that fact when we continue. As we continue, notice that there is a factor of 2 at the beginning of each term. That 2 can be factored out to the front of the area expression, leaving you with just the 4 fractional parts of the areas of the red, yellow, green, and purple trapezoids. The factor of 2, again, can be factored out to the front. Additionally, every term has a denominator of 2. That denominator of 2 can be factored out to the front in the same way. So now we have 2 over 2 in the front. I'll leave it as 2 over 2 temporarily, even though that's, of course, 1. We have 2 over 2 times the quantity of, and then I have in parentheses the 2 terms from the numerator of the red trapezoid, f of 1 plus f of 3, plus the 2 terms from the yellow trapezoid's numerator, f of 3 plus f of 5, green trapezoid, f of 5 plus f of 7, and the purple trapezoid's numerator was f of 7 plus f of 9. Now what I'm going to do next is something that is done in the trapezoidal rule. I'm going to notice that the end of the term for the area of the red trapezoid is f of 3, and the beginning of the two terms for the area of the yellow trapezoid is also f of 3. Mentioned that earlier. F of 5 is the second term in the yellow trapezoid's area and the first term in the green trapezoid's area, and there's also a repeat of f of 7. Each consecutive trapezoid's area formula ends the same way the next one starts. And you can use that fact to somewhat compact this expression. What I've done here is just simply brought down the first term f of 1, but then because there are two f of 3 terms, I've written it once with the coefficient of 2. There are two f of 5 terms, I'll write it once with the coefficient of 2. The f of 7 terms pair up, there's two of those, and the last term, the final term, f of 9, is solo. There's not a coefficient in front of that. The very first term and the very last term, there's only one of those, but the rest of them came in pairs. With this expression simplified, let's go ahead and find an approximation for our area between the curve f of x equals x squared plus 1 and the x-axis from x equals 1 to x equals 9. And again, we're doing this by finding the area of 4 trapezoids drawn right under the curve. So what I'll do is I'll go ahead and simplify this 2 over 2 to be 1, and then evaluate f of 1, which is 1 squared plus 1, which is 2, and then 2 times f of 3 is 10, f of 5 is 26, f of 7 squared plus 1 is 50, and then f of 9 squared plus 1 is 82. Multiplying those three middle terms by 2 gives me these 5 terms, and they have a sum of 256. So our approximation for the area between the curve and the x-axis from 1 to 9 is 256 square units using the area of 4 trapezoids to do the approximation. So approximating area with trapezoids would be done generally for a function that could not be integrated from 1 to 9. This one I chose this function to work with because it's a pretty simple function to work with, but you can find the exact area between the curve and the x-axis by integration, by definite integration. Let's integrate x squared plus 1 from 1 to 9. Well, the integral of x squared plus 1 is x to the third over 3 plus x. We'll go ahead and integrate that from 1 to 9. We'll substitute a value for 9 for x, subtract it from substituting a value of 1 for x in the integral, and that yields, the first term is 252, the second one is 4/3, 250 and 2/3. The exact area between the curve and the x-axis from 1 to 9 is 250 and 2/3. Our approximation with trapezoids gave us 256. So it was a pretty good approximation. It's just over 5 square units off. Still a pretty good approximation, especially in comparison with the approximation you would get from inscribed rectangles as opposed to trapezoids. The area you would get if you added up the area of these 4 rectangles is 176. That's a margin of error 15 times greater than what we got with the trapezoids. So again, the use of trapezoids to approximate area between a curve and an x-axis is superior to approximating area with rectangles. Now let's generalize. This is a very important part of the video where we will derive the trapezoidal rule. We're not always going to be integrating a function, a specific function like f of x equals x squared plus 1. Let's generalize to just any function f of x. And instead of saying we're going from 1 to 9, let's say, hey, we're going from some x value a to another x value b. How many trapezoids are we going to use? Well, in our example we just did, we used 4 trapezoids, but the trapezoidal rule can be used with any number of trapezoids. We're going to go again, not from 1 to 9, but from A to B. These are x values. We'll think of the first x value instead of being 1, 2, 3, 4 up to 9. Let's call them x sub 0, x sub 1, x sub 2, x sub 3, the whole way up to some arbitrary x sub n. And we're going to be using the area of a single trapezoid as the trapezoid area formula, which is the width of a trapezoid times the one height plus the second height over 2, basically the average of the two heights. In this generalization, the width of a single trapezoid is the difference between the end of our interval and the beginning of the interval divided by the number of trapezoids. Recall what we did in our example. It went from 1 to 9, so there were 8 units from the beginning to the end, and we used 4 trapezoids of equal width. 8 divided by 4 was 2. Here we're just going to say, okay, well, whatever our ending value is, whatever our ending x value is minus the beginning x value divided by the number of trapezoids, that's the width of each trapezoid. So whenever we add together the areas of all of the trapezoids, the area for the red trapezoid will begin with a factor of b minus a over n. That's the width of the red trapezoid. And the widths of all of these trapezoids are going to be the same. After the width of the trapezoid comes h1 plus h2 over 2, which is the beginning of the trapezoid's height plus the ending of the trapezoid's height divided by 2. For the yellow trapezoid's area, it's going to be the same thing. The width will be the same. Now the two heights of the yellow trapezoid will be different than the red trapezoid, no matter what this function is, but the width, the value of w in the front, will be the same for all of the trapezoids. When we write the formula for the trapezoidal rule, there's going to be a dot, dot, dot in the formula to indicate that this can be used for any number of trapezoids. Now that we have an expression for the area of all of the trapezoids added together, no matter how many trapezoids there are, notice that there are some similarities in each term. B minus a over n, the width of each trapezoid, is the same, and that will start off every term. Additionally, each trapezoid's area formula includes a division by 2, so the b minus a over n and the divided by 2 can both be factored out to the front. I'm going to factor that out to the front of this expression. B minus a over n is factored out to the front, and then because all of the formulas involve a division by 2, I'll factor the 2 out to the front as well. Let's see what we're left with inside of the brackets here. Now, for the red trapezoid, it begins above x sub 0 and ends above x sub 1. So h1 plus h2 for the red trapezoid would be f of x plus 0 plus f of x sub 1. The yellow trapezoid begins at x sub 1, ends at x sub 2. The green trapezoid begins at x sub 2, ends at x sub 3. And then this would be applied for as many trapezoids as you would be working with. Remember, the more trapezoids that you work with, the more accurate your approximation, but the more work you'll have to do. Regardless of the number of trapezoids, we'll end here with what I have as a purple trapezoid, and it ends at x sub n. So let's describe the next to the last one as x sub n minus 1. So that's what the last trapezoid will look like. This is x sub n minus 1, and this is the end, x sub n. Exactly the same thing happens in this expression as did when we were using an actual function and actual values. The end of the area formula for the red trapezoid is the same as the beginning for the yellow trapezoid. The line that represents the ending height of the red trapezoid is the beginning height of the yellow trapezoid. So we can put those two terms together. The end of the yellow trapezoid, the vertical line that represents the height of the end of the yellow trapezoid, is the beginning of the green trapezoid. And that will happen for each subsequent trapezoid, regardless of how many there are. So we can summarize this formula. The beginning, f of x sub 0 in this case, there's only one of those. The beginning of the red trapezoid, that side is not shared with any other trapezoid. The end of the purple trapezoid is not shared with any other trapezoid. But in the middle, there's always going to be two of them. F of x sub 1, that term shows up twice. Let's write it once with a coefficient of 2. F of x sub 2, that's going to show up twice. Even though I haven't continued this expression further, f of x sub 3 would show up twice. And then there'll be as many trapezoids as you want to use. There would always be a coefficient of 2 in front of the next terms until you get to the end. Even the next to the last trapezoid, this is the beginning of the purple trapezoid in this diagram, the beginning of the purple trapezoid, that would be shared with, this side would be shared with the end of the trapezoid that comes before it. So this would have a coefficient of 2 as well. And then the end of the purple trapezoid, that doesn't have a coefficient. That's just f of x sub n without a 2 in front of it. This expression describes the area, the approximation of the area between a curve and the x-axis with trapezoids. And that expression is known as the trapezoidal rule. The trapezoidal rule provides an approximation for a definite integral. The trapezoidal rule states the integral from a to b of f of x dx is approximately equal to b minus a over 2n times the quantity of f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2, and so on until the next to the last term, which has a coefficient of 2, and the last term, f of x sub n, does not have a coefficient. N in this rule is the number of trapezoids used in the approximation. We're going to do an example in a second, but you could use any number of trapezoids. The more trapezoids you use, the more accurate your answer, but the more basically arithmetic you have to do to come to that approximation. Now, let's apply the trapezoidal rule to an example problem. Here, we are being asked to approximate the integral from 2 to 5 of 6 plus x squared dx with the trapezoidal rule. And look, n equals 6. They're asking us to use 6 trapezoids in our approximation. Now, I'm not going to graph f of x equals 6 plus x squared, and I'm not going to draw any trapezoids, but the trapezoidal rule, applying the trapezoidal rule, will give me the result, the approximation of what would happen if I did, and then added together the area of those 6 trapezoids. But all that I have to do is apply this trapezoidal rule that we just derived, and that will give us the approximation. Now, the trapezoidal rule isn't as hard to apply as it looks. This looks like sort of a big complicated formula, but it's actually pretty easy, pretty straightforward to apply. The integral from 2 to 5 of 6 plus x squared dx is approximately equal to, by the trapezoidal rule, 3 over 12. The beginning, the first part, is fairly easy. b minus a over 2n is 3 over 12 because b minus a, 5 minus 2, is 3, and 2n, where n is the number of trapezoids being used, is 12. And then we're going to have some brackets and some terms added together inside of those brackets. The number of terms in the brackets is always one more than the number of trapezoids you're using in the approximation. Here we're using 6 trapezoids. There will be 7 terms in the brackets. These 7 terms are all added together. And the first term and the last term are the easiest. The first term is f of the lower bound, in this case f of 2, and the last term is just f of the upper bound. F of 5 is the last term. The terms in the middle are a little bit more complicated to come up with. These are the terms that all have a coefficient of 2. The terms in the middle, they will all have a coefficient of 2. And to be able to determine what value you're going to evaluate in the function in these middle terms, you have to know the width of a single trapezoid. You have to know how far to go from the beginning of the first trapezoid to the end of the first trapezoid, and so on. You can find the width of a single trapezoid by just subtracting the beginning and end of the x values on the x-axis that you are finding the area of, in this case 5 minus 2, and then dividing by the number of trapezoids you're using, in this case 6. 5 minus 2 over 6 is 3/6, or 1/2, 0.5. So what that means is the width of each trapezoid is 0.5. So the first trapezoid will start at f of 2 and end at f of 2 plus 1/2, will end at f of 2.5. So that next term will be 2 times f of 2.5. And you know that you go from 2 to 2.5 in the function by finding the width of a single trapezoid using b minus a over n. Each subsequent term will increase by 1/2 unit. So I'm going to go from f of 2.5 to the next term, f of 3. And then from f of 3 to f of 3.5 to f of 4 to f of 4.5. And if I've done everything correct, another 1/2 of a unit above 4.5 will be the ending, the upper bound in this definite integral, 5. You can see that is the case here. So this expression has applied the trapezoidal rule correctly. Now we have to do some computations to get to our answer. In my opinion, at this point, the hard work is done. We're just left with some basically arithmetic to determine our approximation using the trapezoidal rule. We'll have to carefully evaluate f of 2, f of 2.5, f of 3, and so on. Evaluating the functions, f of 2 is 10, 2 squared plus 6 is 10, f of 2.5 is 12.25. You see the results of f of 3, f of 3.5, and the other functions on the screen. The middle 5 terms each include a factor of 2. So next I'm going to perform those multiplications. And that leaves me with these 7 terms. 2 times 12.25 is 24.5. 2 times 15 is 30, and so on. The only thing that changed from the second to the third line is I multiplied the middle 5 terms all by 2. And then there's an addition. There's an addition. Adding those 7 terms yields 228.8. And that, after being multiplied by 1/4, is 57.125. An approximation of the definite integral of 6 plus x squared from 2 to 5 is 57.125. This approximation was found by using the trapezoidal rule with 6 trapezoids. To summarize, we just used the trapezoidal rule with n equals 6. We used 6 trapezoids to approximate this definite integral and found it to be 57.125. As I discussed in this video, in general, the trapezoidal rule is used to approximate integrals that would be very difficult, definite integrals that would be very difficult to find otherwise. The actual value of 6, the integral for 6 plus x squared, is not difficult to find. The integral of 6 plus x squared is 6x plus x to the third over 3. And if we evaluate that from 2 to 5, we substitute a 5, and then subtract, substituting a 2 for x, you'll get exactly 57. So the actual value of this definite integral is 57. We came pretty close with the trapezoidal rule using 6 trapezoids. Pretty close. Realize that approximating with 6 rectangles, you may have approximated integrals with rectangles in the past. It gives an approximation, but it's not nearly as accurate, not nearly as close as an approximation with the trapezoidal rule. The trapezoidal rule, once again, provides, the whole reason we use it is it provides a way to fairly accurately approximate definite integrals, and it's useful for definite integrals that cannot be easily evaluated. And the final thing I'll note is that Simpson's rule is another method for approximating definite integrals. I have an example problem using Simpson's rule on my channel, and you can find it, if interested, in the video description below. Thank you for watching. I hope you learned something.